Long before its final flight, Columbia had already become one of the defining machines of the Space Shuttle program. Its early missions demonstrated a central promise of the shuttle concept. An orbital spacecraft could return to Earth, be prepared again, and fly another mission. STS-2 marked Columbia's return to space after its inaugural flight, beginning an operational history that would eventually span more than 2 decades. Every mission ended with the same demanding transition. Columbia had to leave orbit, encounter the atmosphere at enormous speed, withstand intense heating, and surrender its remaining energy during an unpowered descent. There was no opportunity to circle the runway for another attempt. The orbiter returned as a glider, touching down only after its flight path and speed had been carefully managed from orbit to runway. Repeated success made these extraordinary operations increasingly familiar, but familiarity did not remove the physical hazards. Each return still depended on the integrity of the thermal protection system surrounding the vehicle. Without that protection, the shuttle's aluminum structure could not survive the conditions of re-entry. By the landing of STS-28 in 1989, Columbia was an experienced spacecraft. It had repeatedly carried crews and payloads into orbit, then endured re-entry and landing. Each completed mission added practical knowledge. It also contributed to a powerful organizational tension. A system could remain hazardous even while repeated success made abnormal events appear manageable. The shuttle was neither a conventional aircraft nor a simple launch vehicle. It combined reusable and expendable components, thousands of thermal protection tiles, powerful main engines, solid rocket boosters, an external fuel tank, complex flight computers, and extensive ground infrastructure. Its safety depended not on one machine or one team, but on many specialized groups recognizing problems and communicating their significance. Even transporting an orbiter between locations required a purpose-built operation. Columbia could be mounted on a modified Boeing 747 shuttle carrier aircraft, turning two large aircraft into a single transport system. Flight crews, engineers, technicians, mission controllers, analysts, contractors, and program managers all occupied different positions within the wider shuttle organization. This division of expertise was essential. No individual could personally monitor every system or understand every piece of evidence. Information had to move between teams. Technical uncertainty had to be translated into decisions. That process worked only when concerns reached the people with the authority and resources to investigate them. Inside Columbia, the complexity became visible. During STS-58 in 1993, pilot Rick Searfoss was photographed in the commander's seat, reviewing a procedures manual. A laptop on the instrument panel displayed a map of Earth, the shuttle's orbital ground track, and the boundary between day and night. The image records an earlier mission, not STS-107, but it reveals the environment shared by Columbia's crews. The flight deck combined physical controls, displays, portable computers, written procedures, and windows looking into space. Astronauts worked within a vehicle whose normal operation required constant reference to checklists, timelines, and information supplied from the ground. Not every problem in orbit involved the dramatic forces of launch or re-entry. During STS-55, Columbia's crew discovered a water leak beneath the mid-deck floor. Access panels and lithium hydroxide air filters were removed so the astronauts could reach the water tanks. Mission Specialist Jerry Ross recorded the work, while pilot Terrence Hendricks entered the access area to search for the source and carry out repairs. The incident illustrates an important feature of shuttle missions. Astronauts were not merely passengers. They operated experiments, monitored systems, maintained equipment, and responded to faults within the limits of the tools, procedures, and information available to them. Technology aboard Columbia continued to evolve. On STS-80 in 1996, mission specialist Tom Jones used a light pen with closed-circuit television monitors while testing the orbiter space vision system. A payload and general support computer formed part of the experiment. Equipment like this extended what a crew could observe and control, but it also produced specialized streams of data. Understanding those streams depended on context. A reading, photograph, or engineering calculation did not automatically become a decision. It had to be noticed, interpreted, compared with experience, and communicated clearly enough to prompt action. Later in the same mission, Jones was photographed holding a map of Australia marked with observation targets, with a 70mm camera nearby. Columbia was both spacecraft and working laboratory. Its missions demanded close coordination between orbital position, scientific objectives, camera operations, experiment schedules, and the everyday management of the vehicle. This was the world in which shuttle flight became routine. It was never simple and never free of danger, but it was organized through training, procedure, experience, and thousands of decisions made on the ground and in orbit. During STS-87 in 1997, pilot Steve Lindsay worked on Columbia's aft flight deck, surrounded by 5 portable computers supporting the video guidance system. The arrangement shows how much information could be brought into the cockpit, and how dependent a mission was on identifying which information mattered. That distinction would become crucial. Engineering organizations rarely fail because no information exists at all. More often, fragments of evidence are distributed among different people. Their significance may be uncertain. Previous experience may encourage a less alarming interpretation. Requests for additional evidence may be weighed against cost, time, operational limits, or an assumption that the outcome is already understood. Another image from STS-87 records computers and a hand controller used with the ER-CAM Sprint robotic camera experiment and its video guidance equipment. It is a final glimpse of Columbia during the long period in which the orbiter served as a platform for increasingly sophisticated work. By the beginning of 2003, Columbia was no longer an experimental newcomer. It was a veteran spacecraft operating inside a veteran program. That history represented immense accumulated knowledge. It also created the conditions in which recurring abnormalities could begin to look less like warnings and more like accepted features of flight. Columbia's final mission would expose the difference between an event that had happened before and an event that was safe. On the 15th of January 2003, Columbia stood at Launch Complex 39A, prepared for mission STS-107. It would be the orbiter's 28th flight, the 113th mission of the Space Shuttle program, and the first shuttle launch of that year. The crew comprised Commander Rick Husband, pilot William McCool, payload commander Michael Anderson, mission specialists Kalpana Chawla, David Brown, and Laurel Clark, and payload specialist Ilan Ramon of the Israeli Space Agency. Ramon would become the first Israeli astronaut. Unlike many shuttle missions of that period, STS-107 was not traveling to the International Space Station. Columbia carried a SpaceHab research module in its payload bay and was scheduled to remain in orbit for 16 days. More than 80 international experiments covered physical science, biology, medicine, technology, and observations of Earth and the Sun. The research program required continuous work. The astronauts were divided into 2 shifts, allowing experiments to operate around the clock. Investigations examined combustion and fire suppression in microgravity, the behavior of fluids and granular materials, protein crystal growth, biological responses to weightlessness, bone formation, immune function, and methods that might later support other spacecraft. Columbia had been modified repeatedly during its long career, but it remained heavier than the younger orbiters and lacked the equipment then required to visit the International Space Station. For STS-107, that was not a disadvantage. The flight had been designed as a self-contained scientific mission, with the crew, space hab module, and supporting equipment forming an orbiting laboratory. Nothing visible as Columbia waited on the pad revealed the chain of events that would follow. The critical damage did not exist before launch. It would be created during the first minutes of flight. At 10:39 in the morning, Eastern Standard Time, on the 16th of January, Columbia lifted off. The countdown had proceeded without a major interruption, and the shuttle climbed away from Florida on a column of exhaust, carrying its 7 astronauts towards orbit. 81.7 seconds after liftoff, a piece of insulating foam separated from the external tank's left bipod area. The bipod structure helped connect the orbiter to the tank. Its foam covering was intended to prevent ice formation and protect the hardware. It was never intended to strike the spacecraft. Launch cameras recorded the foam crossing the gap between the tank and Columbia. It hit the underside of the orbiter's left wing, near its leading edge. The shuttle continued climbing, and its engines operated normally. There was no cockpit alarm capable of telling the crew that the wing's protective structure might have been breached. The object was lightweight compared with metal debris, but mass alone did not determine the possible damage. Columbia and the foam were moving relative to one another at high speed. The wing's leading edge was protected by panels made from reinforced carbon-carbon, a material designed to tolerate the extreme heat of atmospheric entry. It resisted heat, but it was not invulnerable to a sufficiently energetic impact. Foam loss was not unknown within the shuttle program. Material had separated from external tanks on earlier flights, and previous strikes had damaged thermal protection tiles. Because those events had not destroyed an orbiter, the recurring anomaly had gradually become associated with a history of successful missions. Past survival was being treated, both implicitly and explicitly, as evidence that the next occurrence would also be survivable. The launch video did not immediately reveal the precise impact point or the condition of the wing. Engineers reviewing the footage could see that foam had struck Columbia, but the available images could not show them the inside of the leading edge. The central question was not whether a strike had occurred. It was whether the impact had opened a path through the thermal protection. That distinction mattered because the shuttle's exterior did more than shield it from ordinary heat. During re-entry, the air ahead of Columbia would be compressed and heated until it formed an intensely hot flow around the vehicle. The reinforced carbon-carbon panels along the front of the wing were the barrier preventing that energy from entering the aluminum structure behind them. Damage to a tile on a less exposed surface and a hole in a leading-edge panel were not equivalent hazards. One might produce local heating that the vehicle could survive. The other could allow superheated gas to enter the wing, attack its internal structure, damage wiring and sensors, and progressively weaken the spacecraft from within. Columbia reached orbit as planned. To the crew and most of the teams supporting them, STS-107 had begun successfully. The experiment started, the two-shift schedule took effect, and the mission settled into continuous scientific work. The unresolved evidence remained in the launch recordings. Images could have transformed that uncertainty, but only if they showed the right part of Columbia in sufficient detail. Ground-based optical systems could observe a shuttle in flight, yet distance, angle, lighting, and resolution imposed severe limits. A recognizable image of an orbiter was not necessarily a diagnostic image of its wing. Within NASA, Specialists analyzed the launch footage and attempted to estimate the foam's size, speed, and point of impact. Their work involved incomplete evidence and assumptions about materials under conditions that could not be inspected directly. Some engineers wanted higher-resolution images of Columbia in orbit. Those images might have helped determine whether the left wing had suffered serious damage. Requests for outside imaging assistance moved through an organization divided by roles and authority. The issue was discussed, but no authorized request produced the detailed inspection the assessment team needed. Analysis continued without a clear view of the wing. This did not mean that everyone knew Columbia was fatally damaged and chose to ignore it, nor did it mean that no one was concerned. Different groups held different pieces of information and interpreted the risk through different experience. The technical possibility of severe damage existed alongside a program history in which foam had fallen before, and every previous shuttle had returned. The crew were informed about the strike, largely so they could answer possible questions after landing. The message they received reflected the prevailing assessment that the event did not represent a safety-of-flight problem. From inside Columbia, there was no practical way to see the relevant section of the left wing directly. Even if a breach had been confirmed, the available choices would have been extraordinarily difficult. STS-107 was neither equipped nor positioned for a normal rendezvous with the International Space Station, and no established procedure existed for repairing major reinforced carbon-carbon damage in orbit. But uncertainty about possible remedies did not make the condition of the wing irrelevant. Before any options could be judged, the danger first had to be understood. For 16 days, Columbia continued operating as a research spacecraft. Data flowed to investigators on Earth, experiments progressed, and the mission appeared successful. Yet embedded within the left wing was a question raised by the launch imagery and left unresolved by the organization. The answer would come only when Columbia encountered the atmosphere. On the 1st of February, 2003, Columbia began its journey home. The mission had completed its planned research program, and the crew prepared the orbiter for re-entry and landing at Kennedy Space Center. A video camera inside the cabin recorded part of those preparations. Commander Rick Husband and pilot William McCool worked through the procedures from the forward flight deck. Kalpana Chawla and Laurel Clark were also visible as the crew secured equipment and put on their pressure suits. The recording is calm because, at that stage, the information available inside Columbia gave the astronauts no clear reason to expect a catastrophe. Their conversation concerned normal entry tasks. The damage beneath the left wing had remained outside their direct view throughout the mission. Columbia crossed the formal boundary of atmospheric entry at an altitude of approximately 400,000 feet. It was traveling at about 25 times the speed of sound. The orbiter's nose rose into the airflow, exposing the reinforced carbon-carbon panels and thousands of thermal protection tiles to rapidly increasing heat. During a normal entry, the shuttle did not simply fall towards the runway. Its guidance system commanded a series of banking turns. These controlled the rate at which the vehicle lost speed and altitude, while distributing heat across its surface. As the atmosphere thickened, the launch damage became decisive. Superheated gas entered through the breach in the left wing's leading edge. Once inside, it attacked components that had never been designed for direct exposure to re-entry temperatures. The cabin video ended before the crew received any unmistakable indication of the developing failure. Nothing in the surviving recording shows them discovering the breach or understanding that the wing was being destroyed. What followed must instead be reconstructed from ground observations, recorded telemetry, mission control communications, and recovered debris. In mission control, the first signs did not arrive as a complete explanation. They appeared as individual measurements behaving abnormally or disappearing altogether. Sensors in the left wing began to fail. Temperature readings associated with the hydraulic system were lost. Other instruments stopped reporting as damage spread through the wing. From the ground, each missing value could initially resemble a sensor fault or communications problem. Together, they formed an increasingly serious pattern, but controllers could not see the physical destruction behind the data. Outside the orbiter, observers began recording pieces separating from Columbia. The vehicle was still traveling across the western United States towards Florida. Its flight control system continued commanding adjustments as aerodynamic forces on the damaged left wing changed. The crew then received indications involving tire pressure measurements on the left side. Mission Control called Columbia to discuss the messages. Husband began to respond, acknowledging the communication, but his transmission ended before the sentence was complete. Controllers tried again. There was no intelligible reply. For a short time, Mission Control continued treating the event as a loss of communications. That response followed procedure. Radio contact could be interrupted, telemetry could be lost, and controllers could not declare the vehicle destroyed merely because its signal had disappeared. Columbia, however, was no longer maintaining controlled flight. The internal damage had weakened the left wing, while the shuttle was exposed to immense aerodynamic and thermal loads. As the wing deteriorated, the flight control system could no longer compensate for the imbalance. The orbiter broke apart over Texas, approximately 16 minutes before its planned landing in Florida. Mission Control continued calling Columbia. Teams searched for tracking information and attempted to restore contact through the available ground stations. The expected radar return did not appear. Flight Director Leary Kane ordered controllers to lock their doors and preserve their data. That instruction protected the records needed for the investigation. Computer displays, communications, and written material were no longer simply operational information. They had become evidence. All 7 astronauts were lost. Rick Husband, William McCool, Michael Anderson, Kalpana Chawla, David Brown, Laurel Clark, and Ilan Ramon. The disaster was not caused by a single sensor failure reported during the final minutes. Those readings were symptoms of destruction already advancing through the left wing. Nor did the final loss of communication begin the accident. The initiating damage had occurred during launch, more than 2 weeks earlier. Reentry transformed that hidden damage into a failure the vehicle could not survive. Debris fell across a vast area of the southern United States, with the main field extending through East Texas and into Louisiana. Communities that had expected to witness a shuttle crossing instead heard explosions and found fragments scattered across roads, woodland, fields, and buildings. The immediate response had several objectives. Authorities had to protect the public because pieces could contain sharp materials, explosive devices, or residues from hazardous spacecraft systems. Search teams also had to locate the crew and preserve wreckage whose position and condition might reveal how Columbia had come apart. NASA, federal agencies, state and local authorities, military personnel, emergency services, forestry workers, and volunteers became part of an enormous recovery operation. Residents were warned not to touch or move suspected debris, but to report its location. Each discovery carried potential evidentiary value. A fragment found farther west could have separated earlier than material recovered to the east. Heat damage, deposits, and fracture patterns could help investigators distinguish components damaged inside the wing from those broken apart during the later disintegration. The search expanded across difficult terrain. Teams worked through forests, wetlands, and reservoirs. The scale of the operation reflected the scale of the breakup. Columbia had fragmented while traveling across several states at extreme speed and altitude. Recovery continued for months. Tens of thousands of pieces were eventually transported to Kennedy Space Center, where investigators attempted to identify their original positions on the orbiter. Only part of Columbia could be recovered, but the surviving material would expose important features of the failure sequence. Before that technical reconstruction could begin, the human meaning of the loss was already visible. Makeshift memorials appeared as people left flowers, flags, photographs, and written messages for the crew. The 7 astronauts had traveled aboard one spacecraft, but they brought different histories to the mission. Husband and McCool commanded and piloted Columbia. Anderson led the payload operations. Chawla, Brown, and Clark served as mission specialists. Ramon represented Israel as the mission's payload specialist. Their scientific work was not entirely lost with the orbiter. Much of the mission's experimental data had already been transmitted to researchers on Earth, but the crew who conducted that work would not return with it. The disaster now presented 2 responsibilities that could not be separated. The dead had to be recovered and honored. The spacecraft had to be reconstructed, not as an act of restoration, but to determine why a mission that appeared normal for 16 days had become unrecoverable during its final minutes. Across Texas and Louisiana, thousands of fragments marked the physical end of Columbia. Within them lay the evidence needed to trace the disaster back to the left wing, to the foam strike, and eventually to decisions made long before the morning of re-entry. The search for Columbia became one of the largest ground recovery operations ever undertaken after an aviation or spaceflight accident. Teams moved systematically through the debris corridor, recording the position of each suspected fragment before collecting it. Location mattered. Columbia had been traveling from west to east when it broke apart. Material found near the western end of the corridor was therefore especially important because it could have separated early in the failure sequence. Investigators were looking not only for recognizable pieces, but for evidence of when and how those pieces had left the vehicle. The operation extended across forests, farmland, towns, and bodies of water. Searchers worked in difficult terrain and faced hazards from both the environment and the wreckage. Shuttle components could have sharp edges or contain residues from propellants and other dangerous materials. Recovery personnel also faced a fundamental limitation. Much of Columbia had been destroyed, fragmented beyond recognition, or deposited where it could not be found. The investigation could never depend on recovering the complete spacecraft. Every available fragment had to be documented, identified, and compared with telemetry, photographs, video, and engineering records. The search continued for approximately 4 months. Nearly 85,000 pieces were eventually shipped to Kennedy Space Center. Together, they represented about 38% of the orbiter by weight. Quantity alone could not solve the accident. The task was to turn thousands of isolated objects into a coherent sequence of failure. Inside a Kennedy Space Center hangar, recovered pieces were arranged on a grid corresponding to Columbia's structure. The reconstruction was not an attempt to rebuild a flyable orbiter. It restored the spatial relationship between fragments, allowing investigators to see patterns that were difficult to recognize when each item was examined alone. Sections from the left and right sides could be compared. Investigators studied fractures, melting, deposits, erosion, and changes in color. The central question was whether damage had occurred during the initial penetration of the wing, during the progressive failure inside it, or during the final breakup. The distribution was not symmetrical. Evidence from the left wing showed that extremely hot gas had entered the structure before Columbia lost control. Deposits found on recovered components helped trace the path of that flow. Damage became more severe towards the area behind the leading edge, where the breach was believed to have formed. The recovery map also supported the chronology. Some of the earliest debris found along the flight path came from Columbia's left side. Ground-based video had recorded material leaving the orbiter before the final breakup, while telemetry showed sensors disappearing within the same wing. No single fragment contained the entire answer. The strength of the conclusion came from independent forms of evidence pointing in the same direction: launch imagery, re-entry telemetry, external observations, debris locations, and the physical condition of recovered material. As more pieces were placed in their approximate positions, the outline of Columbia reappeared across the hangar floor. Large areas remained empty. Those gaps represented components that had burned, shattered, or never been recovered. The reconstruction allowed investigators to test competing explanations. A failure beginning elsewhere in the orbiter would be expected to leave a different pattern. An explosion, engine malfunction, or random structural break would not readily explain the concentration of pre-breakup heating and sensor losses within the left wing. The earliest abnormal telemetry came from that side of the vehicle. Temperature measurements and wiring routes showed the damage advancing inwards. By the time tire pressure indications appeared in the cockpit, the failure had already spread beyond the systems surrounding the wheel well. The breach was located in the reinforced carbon-carbon panels forming the front of the wing. During re-entry, these panels faced some of the highest temperatures anywhere on the orbiter. Behind them was an aluminum wing structure containing wiring, hydraulic lines, landing gear components, and load-bearing elements. Once superheated gas entered that space, the wing was attacked from within. Columbia's external shape could remain recognizable while internal components were progressively weakened. This explained why the orbiter continued flying for several minutes after the first recorded signs of damage. It also explained why the crew had so little useful warning. The instruments reported consequences occurring inside the wing, not a direct diagnosis of the original breach. By the time those consequences reached the cockpit, no procedure could restore the missing thermal barrier. Investigators examined Columbia's major systems, including the recovered main engine power heads. The engines had propelled the shuttle only during ascent and were shut down after Columbia reached orbit. Their conditions still had to be studied. A credible investigation could not simply assume that every system outside the leading explanation was irrelevant. The same principle applied throughout the reconstruction. Telemetry, recovered hardware, and recorded observations were used to eliminate possible explanations as well as support them. The evidence did not indicate that Columbia's main engines had initiated the loss during re-entry. Attention remained on the left wing and the object seen striking it during launch. But there was still a difficult engineering question. Could a piece of external tank foam, a material light enough to be crushed by hand, genuinely break a reinforced carbon-carbon panel? The intuitive comparison was misleading. The foam's low density did not mean that an impact at high relative speed carried little energy. Its shape, orientation, and point of contact also mattered. Calculations and computer models could estimate the result, but the investigation needed physical testing. Engineers constructed tests using pieces of external tank foam and reinforced carbon-carbon panels representative of Columbia's wing. A compressed gas cannon launched the foam at speeds intended to reproduce the impact conditions derived from the launch recordings. Initial tests against less critical thermal protection surfaces demonstrated damage, but the decisive experiment targeted a leading-edge panel. On the 7th of July, 2003, a foam projectile struck a reinforced carbon-carbon panel during a full-scale test. The impact opened a large hole. The result directly challenged the argument that foam was too light to cause catastrophic damage. Under the relevant conditions, it could breach the material protecting the wing's leading edge. The test did not reproduce every detail of the original strike with absolute certainty. Investigators could not recover Columbia's missing panel in a condition that revealed the exact opening. Even so, the experiment showed that the proposed failure mechanism was physically credible. The evidence now formed a continuous chain. Foam separated from the external tank during launch and struck the left wing near its reinforced carbon-carbon leading edge. The impact created a breach or serious damage in that region. Columbia then spent 16 days in orbit, where the opening produced no equivalent thermal threat. During re-entry, hot gas penetrated the wing through the damaged protection. It eroded the internal structure, destroyed sensors, and altered the wing's aerodynamic performance. Columbia's flight control system attempted to compensate, first through changes to its control surfaces, then with additional commands from the reaction control system. Eventually, the damage exceeded the system's ability to maintain stable flight. The weakened wing failed, and the orbiter broke apart. That was the physical explanation. It answered how Columbia was destroyed. It did not explain why a known strike had not been treated as a possible threat to the crew. Nor did it explain why better images had not been obtained, or why recurring losses of external tank foam had remained acceptable within a program responsible for human life. Those questions led beyond the wreckage in the hangar and into the structure of NASA itself. During STS-107, responsibility for assessing the foam strike passed through several parts of NASA. Engineers formed a debris assessment team to analyze the launch imagery, estimate the impact, and determine the possible consequences. Their work took place within a management structure that controlled access to resources and decided which concerns required action. Linda Ham chaired the mission management team, which coordinated decisions affecting the mission as a whole. Ham did not cause the foam to separate, and the later investigation did not reduce the disaster to the actions of one manager. Her role nevertheless placed her within the chain through which technical uncertainty was interpreted and converted into operational decisions. The launch recordings could not reveal the condition of the left wing in sufficient detail. Engineers therefore worked with estimates, attempting to determine the foam's dimensions, speed, trajectory, and likely impact point. Small changes in those assumptions could produce very different predictions of damage. A software tool called Crater was used to estimate possible harm to the thermal protection tiles. It had not been designed to model a large foam impact against reinforced carbon-carbon panels. The analysis therefore contained uncertainty from the beginning. Some results predicted tile damage deeper than the tile itself, indicating that the model was being applied beyond the range for which it had been validated. Engineers discussed obtaining high-resolution images of Columbia from national defense assets. Such images might have clarified whether the wing's leading edge or underside showed major damage. Requests were initiated through informal and incomplete channels, but no authorized request produced the detailed inspection the assessment team needed. The process exposed a difference between asking a technical question and having the organizational authority to pursue it. Engineers could identify uncertainty, but they could not independently redirect military imaging systems. The request had to pass through managers, who first had to accept that the uncertainty justified further action. Mission managers believed the foam strike was unlikely to threaten the crew's safe return. Previous missions had experienced foam loss and tile damage without losing an orbiter. That history shaped the interpretation of the new event. But the reasoning contained a dangerous reversal. The fact that earlier foam strikes had not caused catastrophe did not demonstrate that foam loss was safe. It demonstrated that the program had repeatedly survived an event its own design requirements did not permit. The possible consequences were also discussed in a way that weakened the incentive to investigate. If nothing could be done to repair serious damage, some argued that additional imagery would not change the mission's outcome. Yet without determining Columbia's condition, NASA could not reliably assess possible responses, prepare the crew, alter the entry plan, or evaluate whether any extraordinary rescue option existed. The crew received a message acknowledging that photographs showed a foam impact during launch. It also told them that the event was not considered a concern for entry. That assurance reflected the management conclusion reached on the ground. It was not based on a direct inspection of the wing. When Columbia was lost, the unanswered engineering question became central to the accident. The vehicle had suffered potentially critical damage, but the organization had closed its assessment before obtaining evidence capable of ruling out that danger. The Columbia Accident Investigation Board was established to determine not only what had physically destroyed the shuttle, but why NASA's systems had allowed it to happen. The board was chaired by retired United States Navy Admiral Harold Jamin. Its investigation drew on launch video, telemetry, recovered wreckage, impact testing, internal communications, engineering analyses, interviews, and records from earlier shuttle missions. The board's final explanation separated the accident into a physical cause and organizational causes. Neither could be understood properly without the other. The physical cause began with foam from the external tank striking the left wing and damaging its reinforced carbon-carbon protection. During re-entry, the breach allowed superheated gas into the wing, leading to structural failure and loss of the vehicle. The organizational findings reached further back. Foam loss had occurred before STS-107. It violated the intended behavior of the external tank, yet missions continued after earlier strikes failed to produce a catastrophe. An abnormal event had gradually become normalized. This did not mean NASA had formally declared every foam strike harmless. It meant operational experience had changed how the hazard was perceived. Each successful landing after a previous strike made the next occurrence easier to classify as a maintenance concern rather than a threat to the mission. The board found weaknesses in the way concerns traveled upwards through the organization. Engineers had incomplete data and limited access to decision makers. Managers expected technical teams to prove that the spacecraft was unsafe, even though the missing evidence made such proof impossible. The more protective question would have been whether NASA could demonstrate that Columbia was safe to bring home. Schedules and program pressures formed part of this environment. The shuttle was supporting construction and operation of the International Space Station, and future missions were arranged within a demanding flight sequence. The investigation did not claim that a launch deadline mechanically caused one particular decision. It found that resource, schedule, and organizational pressures influenced how risk was understood and communicated. Communication also became fragmented. Concerns expressed in engineering discussions did not always reach the mission management team with their original force or uncertainty intact. Presentations compressed complicated technical work into simplified conclusions. The absence of definitive proof of catastrophic damage was too readily treated as evidence that catastrophic damage had not occurred. The board compared aspects of this organizational behavior with conditions preceding the Challenger accident in 1986. The technical mechanisms were different. Challenger was lost after the failure of a solid rocket booster joint. Columbia was destroyed after damage to its thermal protection system. The recurring institutional problem was the treatment of warning evidence under uncertainty. 17 years after Challenger, NASA again possessed pieces of information that did not produce an adequate safety response. Expertise existed. Concern existed. What failed was the system for turning concern into an authoritative investigation before the vehicle and crew were committed to the hazard. The board therefore rejected the idea that Columbia resulted from a freak impact that no organization could reasonably have anticipated. Foam shedding was known. The strike was recorded. The limitations of the available images were understood. What remained unknown was the actual condition of the wing, and NASA accepted that uncertainty without resolving it. The report concluded that changing individual procedures would not be enough. Hardware had to improve, but so did the conditions under which engineers raised concerns. Managers evaluated uncertainty, and the agency learned from anomalies. Before the shuttle could return to flight, NASA had to address the immediate technical hazards identified by the board. External tank foam loss had to be reduced. Launch imagery had to improve so damage could be detected and assessed. The orbiter needed the ability to inspect critical surfaces in space, rather than depending solely on distant ground cameras. Later missions used additional cameras and radar to observe ascent. Astronauts employed an inspection boom carrying sensors capable of examining the wing's leading edges and thermal protection surfaces. Crews also performed a maneuver beneath the International Space Station, so its occupants could photograph the orbiter's underside before docking. NASA developed procedures for analyzing suspected damage and investigated limited repair techniques. A damaged shuttle at the station could remain there, while another response was considered. For missions that could not reach the station, contingency planning had to address the possibility of using another orbiter for rescue. These measures changed the evidence available to decision-makers. A future mission would not have to rely entirely on launch footage of uncertain resolution. Engineers could request targeted views of a suspected impact area and compare them with the vehicle's known condition. The return-to-flight program also required changes in technical authority and safety oversight. Independent safety organizations needed a stronger voice. Engineering concerns had to reach decision-makers without being filtered into unjustified certainty. Risk could not be accepted merely because the same anomaly had been survived before. Yet procedures and equipment could not guarantee that institutional memory would endure. Organizations change, experienced personnel leave, schedules tighten, and unusual events can again become familiar. The deeper lesson of Columbia was not a single rule about foam. It was a warning about how evidence is handled when information is incomplete and the consequences of delay are severe. The shuttle fleet eventually returned to flight, but Columbia did not. Its loss permanently altered the program's direction. NASA resumed assembly of the International Space Station while preparing to retire the remaining orbiters once that work was complete. The investigation began with a damaged wing. It ended by revealing another breach, the separation between the people asking whether Columbia might be in danger and the system empowered to find out. While investigators began reconstructing the loss, communities across East Texas gathered to remember the crew. On the 8th of February, 2003, thousands attended a memorial in Lufkin, one of the centers of the debris recovery operation. People across the region had been drawn into the disaster without warning. Wreckage had fallen across their towns, roads, fields, and forests. Residents reported fragments, assisted search teams, and confronted the physical remains of a spacecraft that had disintegrated above them. Their response became part of the recovery itself. Evidence that might otherwise have disappeared was identified and protected. The investigation depended not only on NASA and federal agencies, but on local knowledge, emergency services, volunteers, and communities willing to support a long and difficult search. The memorial transformed a debris field into a place of collective remembrance. The 7 people aboard Columbia were no longer distant figures seen only through mission broadcasts. Their final journey had ended over these communities. The funerals that followed returned attention from the spacecraft to the individuals who had flown aboard it. Rick Husband was a United States Air Force colonel and commander of STS-107. William McCool, a United States Navy commander, served as pilot. Michael Anderson was the mission's payload commander. Kalpana Chawla, David Brown, and Laurel Clark were mission specialists. Ilan Ramon, a colonel in the Israeli Air Force, flew as payload specialist and became Israel's first astronaut. They were engineers, scientists, physicians, military officers, pilots, and researchers. During 16 days in orbit, they completed a demanding program of scientific work conducted around the clock. Much of the resulting data had already been transmitted to Earth before Columbia was lost. No technical explanation could reduce the significance of their deaths to a sequence of failed materials and damaged systems. The investigation mattered because decisions made within complex organizations ultimately affected 7 human beings who depended on that organization to identify dangers they could not see for themselves. Columbia's loss also confronted NASA's leadership, with a duty extending beyond the immediate investigation. The agency had to preserve the crew's memory while ensuring that remembrance did not become a substitute for institutional change. Sean O'Keefe was NASA administrator when the accident occurred. In the years that followed, Columbia memorials became places where leaders, employees, and families could return to the meaning of the loss. Their importance lay not only in mourning, but in maintaining a visible connection between technical work and its human consequences. Spaceflight organizations routinely deal with probabilities, component tolerances, test results, and risk classifications. Memorials restore what those abstractions can conceal. A risk accepted on paper is ultimately accepted on behalf of a crew. The astronauts' families remained part of Columbia's legacy. Their relationship with NASA continued after the official investigation had ended and the shuttle had returned to flight. No ceremony could compensate for the loss, and no conversation could undo the decisions made during STS-107. Later observances could, however, prevent the crew from being remembered only as the victims of an accident. Their professional lives, research, and contributions to human spaceflight remained larger than the final minutes of the mission. The families' continuing presence also reinforced a difficult standard of accountability. An organization asking people to accept extreme risk must be prepared to examine its own failures openly, preserve uncomfortable evidence, and resist the temptation to turn a complicated disaster into a convenient story about one broken component. Moments of silence became part of NASA's annual remembrance. Silence alone, however, cannot preserve a lesson. Institutional memory requires records, training, engineering discipline, and a culture in which uncertainty can be raised without first being converted into proof. Columbia demonstrated how success can distort the perception of risk. Foam loss had been observed before. Because earlier orbiters returned safely, the repeated anomaly became easier to tolerate. The absence of catastrophe was mistaken for evidence that the process was under control. That pattern is not unique to spaceflight. It can emerge wherever complex systems operate under pressure and small failures recur without immediate consequences. Columbia's warning is that survival does not validate a defective condition. Sometimes it only postpones the moment when the consequences become visible. The loss reached far beyond the United States. Ilan Ramon's flight carried enormous significance in Israel, while Kalpana Chawla remained an inspiration in India, the country of her birth. Memorial ceremonies in different nations reflected the international character of the crew and the research conducted during STS-107. The mission's experiments involved scientists, agencies, universities, and students from around the world. Even after the destruction of the orbiter, transmitted data continued to support research. Columbia's scientific purpose survived in records and results, just as its safety lessons survived in the changes imposed on later shuttle missions. International remembrance also revealed why the accident could not be treated as a private failure within one agency. Human spaceflight is watched, supported, and understood across national boundaries. Its achievements are shared widely, so are its losses. NASA's Day of Remembrance places Columbia alongside the crews of Apollo 1 and Challenger. The three accidents occurred in different vehicles, during different phases of flight, and through different physical mechanisms. Apollo 1 was lost in a cabin fire during a ground test in 1967. Challenger was destroyed shortly after launch in 1986, following the failure of a solid rocket booster joint. Columbia was lost during re-entry in 2003 after launch debris breached its left wing. Keeping those differences clear is essential. Yet each accident also exposed the relationship between engineering evidence and organizational judgment. Hardware failures became fatal within systems where warning signs, assumptions, and decisions shaped what was done before the crew could be protected. Remembrance therefore carries an operational purpose. It challenges each new generation to recognize that major accidents rarely arrive without a history. The evidence may first appear as an inconvenience, an accepted anomaly, or a concern that cannot yet be proved. The opportunity to act exists before certainty. The emblem joining Apollo 1, Challenger, and Columbia does not claim that the accidents were the same. It recognizes a shared obligation to the people lost in the pursuit of spaceflight. After Columbia, shuttle operations continued under new inspection and contingency procedures. Discovery returned the fleet to flight in 2005. The International Space Station was completed with the support of further shuttle missions, and the program ended in 2011. Retirement did not make Columbia's lessons obsolete. New spacecraft use different designs, materials, and operating models, but they remain dependent on people interpreting imperfect information. The technical details change. The challenge of communicating risk does not. Permanent memorials preserve the astronauts. Names after the machinery, programs, and organizations around them have changed. Rick Husband, William McCool, Michael Anderson, Kalpana Chawla, David Brown, Laurel Clark, Ilan Ramon. Their names represent 7 individual lives, not a collective symbol created by the disaster. They also mark the point at which an unresolved engineering concern became an irreversible human loss. The most meaningful tribute is not the claim that space exploration can be made free from danger. It cannot. The meaningful distinction is between risks that are inherent and risks that are allowed to grow because warnings have become familiar, information is fragmented, or uncertainty is mistaken for safety. At the Space Mirror Memorial, the names of astronauts lost in the United States space program are cut into polished stone and illuminated from behind. Columbia's crew occupies a permanent place among them. The sequence that brought them there began with a piece of foam leaving an external tank. But the disaster was not created in 81 seconds, and it cannot be understood through the impact alone. It developed through earlier foam losses, incomplete imagery, uncertain analysis, failed communication, and decisions that closed the question before the evidence justified doing so. Columbia completed its scientific mission. It carried its crew through 16 days in orbit. It survived until the final passage through the atmosphere exposed the damage hidden inside its left wing. The investigation recovered only part of the spacecraft, yet it recovered enough to establish what happened. The harder task was to understand why. That answer reached beyond materials and aerodynamics into the way institutions perceive risk. A warning does not become harmless because it has been survived before. Uncertainty is not evidence of safety, and when human lives depend on the answer, the absence of proof is not permission to stop looking.